Can you hear me? Yes, in the back. Brandon? So please take a seat. Thank you for coming to the session before lunch. I'm going to try to keep it a little bit less technical than the previous two talks. So what have we seen so far? We've seen that there are computationally efficient algorithms for robust high-dimensional estimation. Okay, that was the sort of conceptual message of the first two talks. And in fact, by using sophisticated algorithmic machinery like higher moments, sum of squares, and other algorithmic techniques, we can actually get pretty surprising results, results that were very far of what was achievable beforehand. Now the question is, okay, we can do these algorithms, but can we solve everything? So is it the case that for every robust estimation problem, we can actually reach the information theoretic optimum in terms of the robustness guarantee in polynomial time, like yes or no? So this talk is going to attempt to give an answer to this question. So obviously the answer depends on the setting. In some cases it's yes, some other cases it's probably no. So this is joint work with Daniel Kane and Alistair Stewart. So let me remind you the setting. We want to develop robust algorithms for high dimensions. We want the algorithms to be tolerant to a constant fraction of corrupted data. So the epsilon, the fraction of corruption, is going to be a constant dependent on the dimension throughout this talk. And the contamination model, the model of corruptions, let me remind you, what this is exactly the same thing as before. So we have a family of high-dimensional distributions. We get samples from a distribution f prime, which doesn't necessarily belong to the family, but it's epsilon close in total variation distance to some unknown distribution f in the family. So this is more or less equivalent to the setting where we have an adversary that corrupts an epsilon fraction of samples. All right, so that's the definition of corruption we're going to use more or less for this talk. So the definition is clear, I hope. So now the generic problem for this talk is going to be the unsupervised learning problem. So we get samples from a model with unknown parameters. We want to estimate those parameters. The first question one would ask, is there an efficient learning algorithm to do this? But in reality, there is a sort of a more refined question. So there are three criteria I'm going to be interested in. One of them is sample size. So we can certainly prove information theoretic lower bounds for that. The second is running time, and the third is robustness in the sense that I defined it. So the generic question we want to ask is, can we minimize or optimize all these three criteria simultaneously? Is it the case that we can always achieve the information theoretic minimum sample size with a polynomial time algorithm that is also optimally robust? It would seem that the answer is yes from a distance based on what you heard from the previous talks, but if you look a little bit closer, the answer turns out to be most likely no. Let me give you a concrete example. So the most basic high-dimensional robust problem, so you get samples, epsilon corrupted samples from a distribution which is a Gaussian with identity covariance and unknown mean vector, so the only parameter is the mean vector. And your goal is to find some hypothesis, not necessarily a Gaussian, but it could be a Gaussian, such that the total variation distance between the hypothesis and the true hidden distribution, the one before the corruptions, is O of epsilon. Epsilon, again, is a fraction of the corruptions, and it's going to be a constant, like 20%. So this problem has been extensively studied until very recently. The best guarantee we could have in terms of the total variation distance, or I guess I should say here the distance between the means, was something like epsilon times root dimension, which is really bad when the dimension increases. And two works were able to make simultaneous progress on this problem and get, so the best thing that we know so far is an error guarantee in the mean or in DTV, which scales as epsilon times the square root log of 1 over epsilon. So completely independent of the dimension, almost linear in epsilon, so almost as good as one would hope, but still there is this root log here, which is annoying. Like, why does it exist? And the question is, can we improve it? Can we actually remove the root log? I should note that O of epsilon error is possible information theoretically. So the Tukey median actually gives you this type of error. So it is possible to have an exponential time algorithm that, given an epsilon corrupted sample from a Gaussian, gives you error of epsilon in DTV, or equivalently gives you an estimate of the mean which is accurate within L2 norm of epsilon. All right, so the question is, can we actually improve on the root log? Can we achieve the information theoretic optimum? And here it is. So is there an efficient algorithm, a polynomial time algorithm, that gives us error that asymptotically beats what the previous algorithms could do? So is the question clear? If there's any question, that's a good time to ask.
Okay.
Yes?
So the sample size is not appearing in any of this?
It is not, and there is a reason for that. So we can actually, because I don't want to talk about minimax, but since you ask, I'll oblige. So the minimax rate for this problem is something like, within constant, epsilon plus root dimension over number of samples. Okay? So when this goes to infinity, n goes to infinity, this goes to 0, I really care about this term. So previous algorithm could do epsilon root d plus the same thing. The algorithms that we got 2 years ago can give you epsilon root log 1 over epsilon plus the same thing. So in reality, I really care about the term that depends on the misspecification. It does not go to 0 when the sample size goes to infinity. So I'm not constraining the sample size at all. You can take as many samples as you like. Of course, polynomially many, otherwise you have to read them. And I really care like how close you can make your error to epsilon.
So our algorithm is still polynomial n, though?
Yes. Yes. So you want, so the n, the sample, yes. But you cannot make n to be like 2 to the d or something, right? It has to be poly d. Okay, so that's the question. Can we remove this root log? Can we improve it asymptotically within any super constant factor? Okay. How do you answer such a question? It's unclear, because these are not problems for which MB hardness is something that can easily be obtained if the problem is indeed hard. So let me give you a family of algorithms for which we can actually prove unconditional lower bounds on the running time. So this is a restricted family of algorithms, it's pretty broad. They're called statistical query algorithms. They're very natural. So instead of actually accessing the data directly by samples, what you do is that you interact with an oracle. So what is this oracle? It's called the statistical query oracle. So what you do is you can ask any question, any statistical query on the data. Okay, so you have a function phi1, it's a predicate. With domain, the domain of the distribution is like bounded, and you can get an estimate of its expectation under the distribution within an additive accuracy of tau. Okay, and you can do this adaptively for as many times as you like. So at the end of the day, you're going to have two parameters of your algorithm. So at the end, after a bunch of adaptive queries of certain accuracy, you'll get an answer, hopefully the right answer. So there are two parameters in the complexity of such an algorithm. One of them is how many queries you ask. And so this is this number q. And the second is what's going to be the accuracy of each query. You don't want the accuracy to be very high. You don't want tau to be very close to 0 because you have to pay for it. If you want to simulate such a query with samples, you would need something like 1 over tau or 1 over tau square samples. If you take the samples, you have to read them. So this sort of would incur a lower bound on the running time just because of that. So the two parameters of statistical query algorithm are the number of queries and the accuracy. So roughly speaking, you can think of the running time being sort of the maximum of 1 over tau and q. Okay? It doesn't matter exactly what polynomial you use, but roughly speaking, this is the model. Is the model clear? So this is an oracle model of computation. So in principle, we can actually prove unconditional lower bounds on the running time of such algorithms. So is the definition clear? Are there any questions? Okay, so how powerful are these algorithms? So the answer is, formally speaking, from a complexity theoretic point of view, we don't know. What we do know is that it's pretty powerful. In particular, a very broad class of techniques in machine learning can be implemented in this model efficiently. Okay, so and this involves like standard results from supervised spark learning and a bunch of techniques that are common in unsupervised learning, including stochastic convex optimization, moment methods, etc. So this was shown in a paper by Vitali, Santos, and co-authors. So there is one algorithm that one person came up with a long time ago that cannot be implemented efficiently in this model, and this is Gaussian elimination over finite fields. The finite field assumption is important here. So this is in many ways an exceptional algorithm that's very, very brittle to errors. And I should say that for all the problems that we're looking at in this talk and previous talks, the best known algorithms are in fact statistical query algorithms. So proving a lower bound for, I guess, this type of algorithms is an indication that the problem might be hard. And in any case, if you want to beat such a lower bound, then you would need to do something genuinely different than what people have been doing for a long time. So given that this is an oracle model of computation, the statistical query model, there is a well-defined notion of dimension, statistical query dimension, that roughly speaking characterizes the running time of algorithms in this model. So there are various definitions of that. So the first one was from Kearns in the 90s, and this paper by Blum et al. For PAC learning in the supervised setting, I think for binary classification. And in this more recent work by Feldman et al., it was generalized to general problems over distributions. So what's the idea? The idea is that you need to define an appropriate notion of inner product, correlation between distributions in your class, which is something like that. I'm not going to explain exactly what this is. And to prove a lower bound, it suffices to construct a large set of distributions in your class that are nearly uncorrelated. So this, every pairwise correlation is going to be small. If you do that, then roughly speaking, the number of distributions that are pairwise uncorrelated is going to correspond to a lower bound on the number of queries of any SQ algorithm for the problem. And the correlation that you get for every pair of distributions in your packing is going to be a lower bound of the accuracy. Okay? That's background. We're not going to need too much this definition of correlation, but this is like standard stuff. So there is the thing that one should remember is that there is a standard methodology to construct lower bounds on the running time of statistical query algorithms by finding a set of distributions that are nearly uncorrelated according to this notion of correlation. Now, so how you do that is another matter. Okay, so this depends on the problem. All right. So now let me state what we can actually prove for this type of algorithms. So the first result answers the question that I posed in the beginning. Suppose that we want to learn the mean of a Gaussian with identity covariance robustly. Epsilon against the fraction of corruptions, and epsilon root log 1 over epsilon was the accuracy of previous algorithms. So the theorem says that if the dimension is large enough, then if you improve the performance guarantee of current algorithms by a factor of m, you should think of m here as sort of super constant, but certainly smaller than root log 1 over epsilon, then the algorithm is in one of two categories. Either it uses queries that have very high accuracy, so the accuracy is going to grow as dimension to the minus this factor m, or the number of queries is going to be at least d to the m, dimension to the number of queries. So the combination of, so what do these two things mean? So suppose you have an algorithm that uses queries of this accuracy. So roughly speaking, this means that in order to actually simulate the algorithm with samples, you would need at least 1 over that many samples, so at least d to the m samples. There, you have to read them, so this, in this case, you get a lower bound of the running time because of the sample complexity. And in the second case, every query needs time at least 1. So if you use this many queries, it means that this is a lower bound on the running time as well. So is parsing the theorem clear? Okay, now what's the message here? The message is that any asymptotic improvement, so m being super constant, in the error guarantee of this previous algorithm would require super polynomial time for algorithms in this model. So that's theorem number 1. So this is a case where there is a gap between what can be achieved information theoretically robustly and what can be achieved computationally efficiently, robustly, at least for this family of algorithms. So that's theorem number 1. Any questions? Yes?
Sorry, I thought that you guys had an improvement to order epsilon from epsilon root log 1 over epsilon.
No. So in the model of corruptions that I have defined, you can actually corrupt your distribution up to total variation distance epsilon. So there's a weaker model of corruption, which is called Huber models, where you take a mixture of 1 minus epsilon times good plus epsilon times noise. Right. In that weaker model, you can get all epsilon.
So the order epsilon is for the Huber model?
Yes.
Oh,
yes. So in the DTV error model, you cannot do that. So this theorem applies for that model. Therefore, there is a separation computationally between these two models. Okay. Anything else? Okay. Yes.
The possibility that you do have a kind of a quasi-polynomial algorithm with a quite a number of samples.
Oh yeah, this is tight also. So if you can get so there is an algorithm that can achieve that guarantee and runs in time d to the m or d to the poly m. Okay, so if you can spend d to the poly log 1 over epsilon samples in time, you can get error epsilon in this error model. So this more or less up to the exponent, the degree of the polynomial in the exponent. This is tight. Yes.
Yeah, I'm just from a high level, is it kind of a proof that says I take information theoretic consideration and get computational complexity law about out of it? Because this family of pairwise disjoint distributions is kind of has nothing to do with computation. It's kind of
right. So okay. So the question is how do you prove that this statistical query dimension is the right thing, right? And indeed, the arguments that show like lower bounds that if the statistical query dimension is large, then your algorithm requires many queries, are of information theoretic flavor. If you are familiar with like Aswat's lemma or tools like that from proving sample complexity lower bounds for estimation, there is some high level similarity. The difference is, like one difference I can explain in 5 seconds, is that in this type of statistical lower bounds, if you have a packing of size m, then your lower bound is something like log m in the sample complexity. While here, if you have a packing of size m, you get a lower bound on the number of queries which is linear or polynomial in m. Okay? Vitaly can answer these questions better than me. So we just used this framework. Yes?
So one quick question. I mean, if you take an algorithm which takes the largest epsilon fraction of your samples and discards them and takes the average, that is not a statistical query algorithm, right?
No, you can't. You can do that. You can actually threshold easily just by taking.
I don't know the threshold beforehand. I look at the data and decide the threshold.
I mean, you can simulate this type of thing with binary search, right? So
Not with these perturbations, right? I don't know spectrum.
is Daniel here? Do you have an answer to that?
I'm not sure exactly what you're asking, but like certainly the algorithm that gets epsilon root log 1 over epsilon is definitely, I mean, it's not immediately a statistical query algorithm, but you can simulate it as a statistical query algorithm with only a small amount of extra work. Basically, once you do your projection, you just, you do a linear, you just like look at a bunch of different thresholds and you see what fraction of points are beyond that threshold, and you use that to find a threshold that works for your filter, and then you apply it.
So Daniel, thank you. So let me give a high-level answer. So the answer is it's not trivial if I give you a polynomial time algorithm for an estimation problem to simulate it by an SQ algorithm that's nearly as efficient. But essentially for all the cases that we know how to do that. So it's not a trivial question of how to do that. So there is no nothing written that does it generically, but empirically we know that it works. Okay, so that's theorem number 1. Yes?
Sorry, this might be a dumb question, but you said this works in the TV model but not in the Huber model?
This particular theorem, yes.
So no, I'm just not understanding. What's the difference between the TV model and the Huber model?
There is a significant difference. So if I have two distributions, let's say P and Q, okay, DTV between P and Q is less than or equal to epsilon, really means that if you take P plus epsilon, let's say P1, is equal to 1 minus epsilon 2 Q plus epsilon 2 Q2, where the sum of this thing is going to be like less than or equal to epsilon. That's what it means. While Huber says that the noisy distribution is going to be 1 minus epsilon Q plus epsilon noise. So the difference between the two is that here, the noise can only, let's say in some sense, add corrupted samples, but not remove samples from the good distribution, while here you can also remove samples from the good distribution, and this is what allows you to prove stronger lower bounds in the more general model. So these two models are not equivalent. Okay, the definition of corruptions is different. Okay? Okay, so let's move on. Now, this theorem is just an instantiation of what we can do in this model, in this SQ model. We can do more. We have a general construction that proves essentially tight statistical query lower bounds for a number of problems. One of them is what I described, like robustly learning the mean of the Gaussian. We have similar results for the covariance. Maybe the most interesting result to show pictures for is a non-robust result, so a lower bound for learning mixtures of Gaussians without noise. And there are some other statistical computational trade-offs. So here is a table. Which line do you like me to explain? Let me explain the one that's not going to appear later, which I think is something that I like. So this one. So the problem here is exactly the same as what I have described so far, robustly learning the mean of a Gaussian. But you have the additional assumption that the mean is k-sparse, so it has at most k non-zero coordinates. Okay, and robustness is important. So how many samples do you need to do that? So you have an epsilon corrupted sample from a k-sparse mean Gaussian, and you want to estimate the mean within epsilon, of epsilon. And then the sample complexity of this problem, of this robust sparse mean estimation, is something like k log d. Okay, let's say epsilon is constant. So we can solve it with k log d samples, but in exponential time. There are known algorithms that were developed subsequently to our first paper by Jerry and by Balakrishnan, Du and Singh in Colts 17, if I remember, that actually use more samples than we need. They use k square, sparsity square log d samples. And the question was if this can be improved. If you can actually get a polynomial time robust algorithm that uses the minimum, the information theoretically optimal sample size. And the answer is no for statistical query algorithms. As one of our results, we show that you cannot improve the k square here for polynomial time SQ algorithms. Okay, so this is one of the lines, so I'm going to show the rest later. All right.
Wait.
Yeah.
On the last line?
The last line is...
So that one you can do in order D samples?
No, you cannot. So,
I mean with a matrix turn-off.
No, you cannot. In the robust case, you cannot.
Okay, just how about, forget robust, just plain old covariance estimation.
So, okay, let me define what this problem is. So what you want to do is output a matrix, okay, which is close to your true covariance matrix in spectral norm, okay? So if you want to do that, you can do this with these samples, all right?
Just in plain old algorithms.
You can do this with these samples even in the robust case, but you cannot do this with a robust algorithm that's polynomial time and uses less than d square samples.
No, forget robustness for a second. I just want to do covariance estimation.
Okay.
What's the upper bound for an SQ algorithm?
Without running time considerations.
It should be polynomial.
Just D.
There's an SQ algorithm that does D?
Yes, yes.
Okay. What is it?
Can I answer?
Yeah.
Okay, thank you. So again, the question here is to robustly estimate the covariance matrix within spectral norm, let's say spectral error 0.1. You can do this with these samples, even with the skew algorithms, but they're not going to be necessarily computationally efficient. So what we show is that if you require computational efficiency, then your SQ algorithm needs to require at least d square samples. Okay? So again, there's a quadratic gap between what is achievable information theoretically and what's achievable with an efficient algorithm. All right? Okay, so the next problem I'm going to talk about is one that has been talked about a lot this morning. Is like I'm not even going to define. So we have a mixture of k Gaussians in d dimensions. Has been extensively studied, and roughly speaking, there are two families of algorithms for this problem. So the first one is when you have separation between the components, and in this case you can get running time which is polynomial in the number of components. When you have no separation, there are sort of exponential lower bounds for sample complexity. So that is sort of a harder version of the problem. But even for the case that you have separation, like non-algorithms cannot cover sort of the general case. So you have if you have a mixture of k Gaussians, not spherical, and you know that every pair of them, every pair of components is going to be almost non-overlapping. The DTV, the total variation distance between the components, is going to be close to 1. Then we don't know how to design an algorithm that runs in time polynomial in the number of components, even though this is information theoretically possible. So, and a related problem is the one of density estimation. We just want to learn the density. There it's pretty straightforward to show that the sample complexity is polynomial in all the parameters without any assumptions. However, the best known running time is still exponential in the number of components. So even though the sample complex is polynomial in K, the best running time is exponential in K. And the question is if this is inherent or not. So why do previous algorithms need that? So an observation is that if you have separated Gaussians, separated mixtures, then density estimation is essentially equivalent to parameter estimation. If you solve the one problem, you solve the other. So the question that you ask is that, okay, suppose we have separated mixtures and you want to do either density estimation or parameter estimation. This is a problem you can solve with poly dk samples. Can you do it in poly dk time? Okay, that's the question. Is the question clear? I think this last slide was probably enough. Okay, so this is a problem for which the information theoretic minimum is something like d times k. The best known algorithm has time d to the function of k. Can we improve the running time of that algorithm to be poly d comma k? And the answer is no for SQ algorithms. So if the dimension is large enough as a function of the components, then any SQ algorithm for this problem either needs to use very, very accurate statistical queries. The accuracy of each query needs to be at least d to the minus k, or the number of queries needs to be exponential in the dimension. Okay? And the message of this theorem is that really the computational complexity of this problem is inherently exponential in the number of components. K is the number of components, even when it's not information theoretically necessary. So the instances that we prove are hard to learn can be learned with a few samples, with k times d samples, but cannot be learned with less than d to the k time. Is the statement here clear?
Can it just undecided by the curse of dimensionality? This is,
it depends, how you phrase these things. The dimension really here is d, and k is the sort of the number of hidden parameters, right? So basically, in which component each sample belongs. But roughly speaking, you could call the number of components something like the dimension of the latent space, but it's informal. And some people might not like it. Roughly speaking, this exponential number of components is a lower bound of the running time, even when it's not information theoretically necessary. Okay, so now let me show how we do this. What is this technique? How do we prove these SQ lower bounds? One advantage of this model is that you can actually prove sort of unconditional lower bounds, and you can give explicit instances that are presumably hard. It's not a reduction from SAT or something. Okay, so I give you an explicit set of instances. So if you don't believe that SQ algorithms are complete, or there is something better, then you should start by solving those instances, those families of instances. So okay, so how does the construction look like? So what's the idea? The idea is that we construct a family of high-dimensional distributions such that the only interesting information about the distributions is hidden in a specific direction of the data, and the hardness of the problem is really finding this direction. To be a little bit more formal, so we construct a family of distributions P sub v, where v is a vector, let's say a unit vector. It's a vector of the unit sphere. So for every v in the unit sphere, we have a different distribution P sub v. And now, what are these distributions? So if we take the projection of the distribution P sub v in the direction of v, then it's some specific univariate distribution that we construct adversarially. And it satisfies this property of step 2, that the univariate projection matches the first m moments of the standard Gaussian. And in the orthogonal complement, in the orthogonal directions to direction v, PV is a standard Gaussian. Okay, it's a very easy type of family. Okay, in the direction of v, if you project the data, it's going to be a distribution A, which has this moment matching property with the standard Gaussian. In the orthogonal complement, PV is going to be a standard Gaussian. All right? So all these are product distributions, okay? But they're product distributions with respect to a non-standard basis. And the hard family of instances is going to be this family of PVs for all V in the unit sphere. So this problem has a name. We didn't know this name when we wrote that paper. We know it now. It's called non-Gaussian component analysis. What you want to do is find the non-Gaussian component in the data. And this non-Gaussian direction has sort of the projection matching the first m moments. All right, so that's the question. So what we prove is that this problem is hard in the following sense, that okay, guess, or maybe let me give you an example. So how does this PV look like? Okay, so this is the formula. If you project it to the direction of V, the projection is this one-dimensional distribution A, and the orthogonal complement is Gaussian. For example, if A is this one-dimensional mixture of 5 skinny Gaussians, then the PV would be something like that. Okay, it's going to be a mixture of high-dimensional Gaussians that are kind of look like parallel pancakes. Okay, and for every A that you pick, you get something different in the high-dimensional setting. And of course, the difficulty here is that you don't know what this direction is, the direction between the means. If you knew that, you would be done, and this is the hard thing to find given samples. So the proposition that we show is that under those assumptions, that if this one-dimensional projection A matches the first m moments with the standard Gaussian, and if there is a net in the space, in particular, if we take 2v and v prime that are nearly orthogonal, the total variation distance between the corresponding distributions PV and PV prime is large, then, let's say bigger than 2 delta, if we want to learn to error delta, so half the separation of the parking, given samples from an unknown sort of PV, then any SQ algorithm for this problem either requires the accuracy of the queries to be very high, like d to the minus m, and m again is the number of matching moments of the one-dimensional projection, or the number of queries is exponential in the dimension. So 2 to the d to the constant. Is that theorem clear? Is the statement clear? So now, given these statements, every lower bound that I had in this table can be obtained relatively easily by constructing a one-dimensional distribution A belonging in the corresponding class of distributions with the property that for some value of m, this matches the first m moments to the standard Gaussian. For example, for the mixtures of Gaussians, indeed, I'm going to take A to look like a bunch of skinny Gaussians far from each other, satisfying some moment conditions. So the point is that once we have this high-dimensional construction, the way that we instantiate it for every problem of interest is solving a one-dimensional approximation theory equation. Okay, so really the interesting conceptually construction is this one. So everything else is like mathematically interesting, but you know, you can work it out. All right. Any questions so far? Yes.
Well, this result, to begin with, you're assuming that the number of samples is, let's say, at least quadratic in the dimension or something. Otherwise,
so I'm not assuming anything here. So the only thing I'm assuming, in fact, formally speaking, in terms of SQ algorithm, there's no such thing as sample size. There's only accuracy of queries and number of queries. So this theorem says something about what's going to be the accuracy and what's going to be the number of queries. So there's nothing like sample. Now, if you ask how would you simulate such an algorithm with samples, indeed, since you have accuracy this high, for each query, you would need something like d to the m samples for every query. But m could be 1, right? In which case, you have d samples. Yes?
What prevents me from having a statistical query about v dot x, or random x, or average of that, or v dot x, for the unknown v, for the correct v?
I don't quite get the question.
So there's one particular v, if I know the v, I'm done, right?
Yes.
So what if my query actually guesses the v and does it?
I mean, you cannot do that. That's the point.
The probability of guessing V is.
It's, so basically, you're going to see in the proof, okay, that you cannot just get random directions. It's not going to work. Okay, so this is going to be the key part of the proof. So let me wait for a few more minutes before I go into that. All right. So yeah, the point is that to solve this problem, you cannot use moments and you cannot use random projections, and I'm going to explain why. And this was the next slide, so I think you're very well timed. So first of all, okay, you cannot use low degree moments here. Why? Because we assumed that this one-dimensional projection A has the exact same first one-dimensional moments with the standard Gaussian, and therefore, each one of those PVs for every V is going to have the exact same m order moment tensor with the moment tensor of n0i. Just by looking at the moment tensor of degree at most m, you get nothing. So you have to look at higher degree, m plus 1. So you have many entries, it's unclear how to use them, how many to sample, which ones, etc. And the second thing is that what Ravi was asking, why can't you use random projections? And the answer is that if you take a random projection, it's going to look very close to a standard Gaussian. Okay? So you would need exponentially many random projections to distinguish your PV for some given V from a standard Gaussian. Okay, let me show the theorem. Okay, so that's the lemma. So this is a little bit technical, so I'm going to only give you a picture. So what does the statement say? Let's X be a sample from PV, where V is some fixed vector, the hidden vector that you're interested in, okay? And let's project X to some direction V prime. And Q be the distribution of the projection. So Q is going to be one-dimensional. So how close is Q going to be to a standard one-dimensional Gaussian? The answer is it's going to be very close. It's going to be something that depends on the angle between the vectors V and V prime and the number of matching moments. So this is certainly always at most 1. If you take a random direction, it's going to be like 1 over root d. So this first term here would be something like d to the minus m. Okay, so the distance, the chi-square distance between a random direction and standard Gaussian is going to be d to the minus m close to whatever. Okay, so it scales with the dimension and with the number of moments that you're matching. Is the statement clear? Does this convince you that you cannot use random directions because you need to use at least d to the m of them? Yes? All right, so how do we prove that thing? So that's really the mathematical core of what we do for this high-dimensional construction. The first question is, okay, so V is the direction that is the hidden one, and V prime is the one that we take. We try to guess what V is, and theta is the angle between them. Can someone tell me what happens if the angle theta is 90 degrees? What is going to be the projection Q? It's going to be Gaussian, right? It's going to be N01. Why? Is that by construction? Because this distribution PV, it's A in the direction of V, and in the orthogonal complement is standard Gaussian. So what we want to show is that if this angle theta is not 90 degrees, but is almost 90 degrees, if these vectors are nearly orthogonal, then the projection is going to be close to Gaussian. That's what this theorem says. So let's see how we're going to do that. So we take the direction of V, we take this is the distribution of the projection of X in the V direction. We take the orthogonal complement where X is Gaussian. And then we take V, we have the two corresponding orthogonal X's. So how would you calculate Q mathematically? The projection of the distribution of V prime dot X. If you wanted to write Q as a density function, how would you write it? All right, so Q is a projection in the direction of V prime, right? So basically what you want to do is you want to integrate over Y prime of the distribution of basically PV, right? And PV, we know that on this plane is going to be a product distribution, so believe me, Q of X prime is going to be this integral, because we have a product structure in the distribution V. And now the only thing that I need to do is relate the coordinate system xy to the coordinate system x prime, y prime. And you do that by using the angle between the vectors. So the Q of X prime, the distribution, the probability density function of the projection of X in the V prime direction is going to be this function. It's going to be a function of A, the distribution that I started from. G is the PDF of the standard Gaussian, and theta is the angle between the vectors. So have you ever seen this quantity in your life? I'm sure you have. In the next slide you'll see why. So this is a linear operator. It's called the Ornstein-Uhlenbeck operator. In computer science we call it Gaussian noise operator. So we have that basically Q of X prime is the application of this linear operator to A with parameter theta. Okay? And the property of this linear operator is that it takes a signal and it smoothens it, it makes it closer to Gaussian. Okay? So everything that we need from this point of the construction was motivated to achieve that. It's just a bunch of calculations that use these properties of this operator, and in particular what we need, we just need the eigendecomposition of this linear operator. We know that the fixed points are going to be essentially the Hermite polynomials multiplied by the standard Gaussian, and then from here everything is pretty sort of easy. Okay? There are some calculations that you need to do that use the fact that A has the exact same first m moments to n01. And that's it for the proof. So I pretend we have already proved this proposition. Let me read it again. that if we have a one-dimensional distribution A that matches the first m moments with the standard Gaussian, and we have a packing, then to learn within error half the distance of the packing, any SQ algorithm needs to either use very high accuracy dimension to the minus number of moments, or use exponentially many queries. So that's the proposition that we prove, and let me show you in the remaining maybe 2 minutes applications. So how do we use that to learn GMMs? So this is what we have shown, and we want to show a lower bound of d to the k for learning mixture of Gaussians. So what does it suffice for us to show? It suffices for us to find the one-dimensional distribution that is a mixture of k Gaussians and matches the first, let's say, k or 2k moments of a standard Gaussian. We can do that using Gaussian quadrature. For this case, the construction is easy, and the one-dimensional construction is going to look like this. All right, so this is going to be your one-dimensional A that you use to prove lower bounds for mixtures of k Gaussians. So since this is the one-dimensional A, how will the high-dimensional distributions PV look like? The answer is they're going to look like parallel pancakes, so they're going to look like this. Let me do this again, because okay. So every distribution in high dimensions, every PV is going to be something like that, and the information you don't know this direction. Okay, so there's going to be some hidden direction. All right, so this is an instance that might seem easy to learn. It's not, okay, because it's very difficult to find this direction. All right, so let me conclude. So what did I give you? I gave you a technique to prove statistical query lower bounds for some unsupervised learning problems involving robustness. The main message is that robustness can make high-dimensional estimation harder. So harder both computationally and information theoretically. So what I showed today is that there are some problems for which we cannot reach the information theoretic minimum in polynomial time. And in terms of future directions, there are many things to do here. So Daniel mentioned a little bit some applications of this framework to a more general version of corruptions where we have that the majority of the data is corrupted. So we have some generalizations of this technique to discrete distributions. So this construction, the way I described it, it uses the rotational symmetry of the Gaussian. We don't really need that. We can generalize it to some discrete distributions that obviously do not have this structure. To some supervised learning problems, we can get the scalar bounds there as well. And there has even been an application to adversarial examples of these ideas. I don't know if Eric is here, but he can tell you about it. Like going forwards, I guess the most open-ended question is, can we find alternative evidence of computational hardness for such problems? So given that NP hardness might be a little bit of a too high a goal, can we prove that these problems are hard for other models of computation? Yes or no, maybe reductions or convex programming hierarchies. And it would be even more interesting if it's not the case, if there is an algorithm that is not a statistical query algorithm and can beat an SQ lower bound. So this depends on the problem. I think it's quite plausible that such problems might exist. I don't know of natural ones. And at this point, I'm going to conclude. Any questions? Yes.
Your framework suggests that all these problems can be reduced to solving this non-Gaussian component. Mm-hmm. So at least you could maybe say that that would be one natural hypothesis, that specific identifying this non-Gaussian component is the hard problem, which we can reduce all these
I mean,
to, and then
but it doesn't go both ways, right? It's not that if you can solve the Gaussian non-Gaussian component analysis, you can solve a generic instance of this problem. It just happens that all these hard instances can be captured by this one hard instance of non-Gaussian component analysis. In particular, there is no reason to use one direction. You can use multiple. It just wasn't useful for this particular applications. There are other problems where it's actually necessary. Some?
Is there any sense in which this packing style propositions, are there converses to them? Like, can you say that if an SQ lower bound holds for this family of instances, then there must have been the structure that you exploited? Is there any, does that make sense?
No.
Like I'm wondering how necessary the approach, or whether this was the only approach to get such a SQ lower bound in some sense. Does the existence of an SQ lower bound?
I think, I don't know the answer to that. Maybe Vitaly can comment on that.
Okay.
But I don't see any other way. Like, I mean, in some sense, what's happening here is that you construct these distributions that are nearly uncorrelated. It means that if I ask a statistical query about any one of them, I learn very little about its relation to the others. So you need some kind of approximate orthogonality property.
Okay.
Right? So the easiest example to think about is if you want to learn parities, where you actually have 2 to the n completely orthogonal ones. But then if you learn that your thing is not a parity, it's not this parity, you don't learn about its relation to any. Basically, you just know that one Fourier coefficient is 0, you don't know anything else about the rest.
Can you just repeat exactly what, regarding this non-Gaussian component analysis problem, what is known or what would be, if you want to get beyond these SQ-based algorithms, what should you try to, so is it about finding this direction when constantly many moments more?
The formulation of the problem, surprisingly, it's exactly what I gave. So you have a distribution that in one direction or in some substop directions is going to match, let's say, it's going to, the m plus 1 moment is going to be different, let's say, by something, and you want to find that direction. So the algorithms that people have developed for this problem actually have this type of behavior. They run in time n samples that scale with d to the m. So I'm being recorded by whatever. So I don't think there is a better algorithm for the generic non-Gaussian component analysis problem, the way that we have phrased it, even if it's not a skew. It just remains to be shown.
Can you say your key lemma again? One of the lemmas was random projection gives you a Gaussian
Yeah, so the point, so let me...
So it looks like if it's that, so does it apply for any distribution at the random?
What do you mean? No, I mean, let me find it. Sorry, guys. I have to go for lunch. So this is the lemma.
Yeah.
So it says that if you take this specific PV, the specific distribution we constructed, that is equal to A in the V direction and Gaussian in the orthogonal complement, and you project it to some other direction of V prime, and you take the distribution of the projection, then the distribution of the projection is going to be very close to a standard Gaussian in one dimension. And therefore, you cannot just hope to take a random direction and hope that the random projection is going to tell you anything. The distribution of the random direction is going to be very close to Gaussian. Right? That makes sense?
Yeah, but I was thinking, in principle, you can construct an algorithm. You have a sparse signal. You can randomly project it, get a Gaussian, and then reconstruct it back. So almost like an algorithm for density estimation. But it looks like it doesn't apply for. I can talk to you offline.
Okay, sounds good. So I think at this point it's a good time to go for lunch. Thanks again, and see you after lunch.